Welcome. Over the next 45 slides, we are going to rebuild whole number arithmetic from the ground up, but at an intermediate level. We will explore why these operations work and how they form the backbone of modern computing, cryptography, and data integrity. It is tempting to think of whole number arithmetic as finished business, but it is far from solved. The security of your digital life, the precision of computer storage, and the accuracy of your financial records all rely on these elementary operations. This course is organized into 6 movements. We will cover everything from foundational place value to modular arithmetic and the open questions that still challenge mathematicians today. Remember, every shortcut we discuss is a consequence of deep mathematical structure. Part 1 is all about foundations. Before we dive into complex arithmetic, we must be precise about the objects we are working with and the positional notation that makes our modern systems possible. A whole number is one of 0, 1, 2, 3, and so on. Note that there are no fractions or decimals involved. 0 is the critical divider between positive and negative numbers on the number line. Always define your conventions clearly. Closure is a fundamental concept in mathematics. It explains why we expand our number systems. When an operation takes us outside of our current set, like division leaving the integers, we invent a new set to accommodate the result. Place value is arguably one of the most important inventions in history. By using position to dictate value, we can represent any number with just a few symbols. This makes written calculation possible, unlike older systems like Roman numerals. Base 10 is just a convention based on our biology. The actual mathematics works in any base. Computers rely on binary for simplicity, while hexadecimal helps humans manage that data, and sexagesimal remains useful for time and angles. Converting between bases is a simple mechanical process. You divide by the target base repeatedly and keep track of the remainders. Reading those remainders in reverse order gives you the representation in the new base. Now, we move to part 2. We will rebuild the 4 primary operations, focusing on the sign rules and structural laws that are essential for advanced problem solving. Using clear terminology is essential. Remember that the sum, difference, product, and quotient are our foundational results. Additionally, be mindful of how you write your work. Standard notation, like dropping multiplication signs, will become increasingly important. The number line provides an intuitive model for signed arithmetic. Movement to the right represents addition, and to the left represents subtraction. These movements clarify why subtracting a negative number is equivalent to adding a positive one. Adding signed numbers is governed by just 2 rules based on the signs of the numbers. Use absolute values to simplify the arithmetic, and always keep track of the result sign. Parentheses can help avoid confusion when operations and signs clash. Subtraction can be simplified by treating it as the addition of the opposite number. By flipping the sign of the subtrahend and changing the operation, you can apply your standard addition rules every time. Multiplication is simply repeated addition. While the commutative property allows us to swap operands, understanding theorem model for multiplication is vital, as it makes the distributive law clear and visually intuitive. Let's discuss multiplication and division rules. The simple version. Same signs result in a positive value, and different signs result in a negative value. A quick shortcut for products is to count the negative factors. An even number of negatives yields a positive result, while an odd number yields a negative result. Next, we explore the division algorithm. Despite the name, it is a key theorem stating that for any dividend and positive divisor, there is exactly one quotient and remainder. This leftover remainder is actually the most useful part, serving as the basis for modular arithmetic and error checking. Why is division by 0 undefined? It's not an arbitrary rule. It's a logical necessity. If you divide a non-zero number by 0, no solution exists. If you divide 0 by 0, there is no unique solution. Because the definition of division requires a unique result, 0 simply doesn't fit. To resolve ambiguity in calculations, we use the BODMAS convention. Brackets of, division, multiplication, addition, and subtraction. Remember that division and multiplication have equal priority and are processed left to right, as are addition and subtraction. Brackets are your most powerful tool to override these default orders. Our mental arithmetic shortcuts are all built on 5 foundational laws: commutative, associative, distributive, identity, and the zero property. The distributive law is the true workhorse of mental math, allowing you to break down difficult multiplication into manageable pieces. Welcome to part 3. We shift our focus to speed and verification. Every technique here leverages those same structural laws to make computation faster and more reliable, ensuring your mental math is based on solid mathematical principles. Mental math isn't just cleverness, it's the deliberate application of the distributive law. Whether you're multiplying by 11, 5, or 25, or handling numbers near a round value, the strategy is always to split the problem into pieces involving powers of 10 to simplify the arithmetic. Russian peasant multiplication is an ancient and fascinating algorithm. It relies only on halving, doubling, and addition, entirely bypassing the need for a memorized multiplication table. It's essentially binary multiplication in disguise, which is how modern processors perform their work. Always estimate before you compute. By rounding numbers to their leading digits, you can quickly check the magnitude of your result. This simple habit helps you spot place value errors immediately, saving time and preventing you from compounding mistakes. Digital roots are a brilliant way to check your work. By repeatedly summing the digits of a result until one remains, you get a quick checksum. If the digital root of your answer doesn't match the digital root of the operations, you know an error has occurred. Let's look at an example. Calculating 7,586 plus 9,492, we compare the digital roots of the inputs and the output. If they don't align, the claim is rejected. This provides a very fast way to verify calculations, catching most errors in seconds. Welcome to Part 4, where we move from performing operations to interrogating numbers. We'll explore divisibility, factors, and primes, the essential building blocks of the whole number system. Divisor, factor, multiple. These are three ways to describe the exact same relationship. We say A is a divisor of B if B divided by A leaves no remainder. A number whose only factors are the trivial ones, 1 and itself, is called a prime number. Divisibility tests allow you to check if a number divides another without performing the full division. Some tests look at the tail of the number, like those for 2, 4, 5, or 10, while others consider all the digits, such as the tests for 3, 9, or 11. Why do digit sum tests work? Because 10 leaves a remainder of 1 when divided by 9. This means every power of 10 also leaves a remainder of 1. Therefore, any number leaves the same remainder as the sum of its digits when divided by 9 or 3. We now explore prime numbers, the atoms of the integer world. Primes are numbers greater than 1 divisible only by 1 and themselves. They appear chaotic locally, but they follow a clear law globally. The count of primes up to a value n is roughly n, divided by the natural logarithm of n. The sieve of Eratosthenes is the oldest efficient method for finding all primes up to a limit. Instead of testing each number, we cross out multiples of known primes. By stopping once we exceed the square root of our limit, we reach a very high level of efficiency. The fundamental theorem of arithmetic is the bedrock of number theory. It states that every integer greater than 1 has a unique prime factorization. This prime fingerprint determines all of a number's properties, from its divisors to its behavior in modular systems. A prime fingerprint allows us to extract deep information without full computation. By adding 1 to each exponent in a prime factorization and multiplying the results, we find the number of divisors. Similarly, we can calculate the sum of all divisors using geometric series. The highest common factor is the largest number dividing a set. You can find it by comparing prime factorizations or by using Euclid's algorithm for larger numbers. The Euclidean method, based on successive remainders, is incredibly fast and avoids the need for full factorization. The lowest common multiple is the smallest number all elements in a set divide into. Using prime factorizations, you take the highest power of every prime present. For two numbers, a quick shortcut is that the LCM multiplied by the HCF equals the product of the numbers. We now move to Part 5, Modular Arithmetic. This is the mathematics of clocks and remainders. We stop throwing remainders away and start treating them as the primary object of study. Two numbers are congruent modulo m if they leave the same remainder when divided by m. This creates a wraparound system. In modulo 12, for example, 17 and 5 occupy the same position. It is the perfect tool for keeping calculations finite and efficient. One of the greatest powers of modular arithmetic is that you can reduce your values at any step. Whether you are adding, multiplying, or taking powers, reducing modulo m at each stage keeps your numbers small, which is essential for massive computational tasks like cryptography. The Chinese remainder theorem tells us that a system of congruences with coprime moduli has a unique solution. This turns remainders into a unique address for a number. It is a powerful technique for simplifying complex calculations by breaking them into smaller, independent pieces. Fermat's little theorem is a cornerstone of modern digital security. It provides a simple test to identify composite numbers by checking if a congruence holds. While it cannot prove primality with total certainty, it is fast enough to handle massive numbers in RSA encryption. We reach part 6. Here, we examine the behavior of whole numbers at extreme scales. We look at exponential growth, factorials, and the beautiful, simple patterns that hide some of the deepest unsolved mysteries in mathematics. Exponents represent repeated multiplication. The laws are consistent. You add exponents for multiplication and multiply them for powers. However, the intuition often fails because exponents grow at a rate that quickly transcends human history, as seen in the classic chessboard doubling problem. Factorials represent the number of ways to arrange distinct objects. They grow faster than exponential functions. We define 0 factorial as 1, which maintains the mathematical consistency of our recursive definitions, allowing us to accurately calculate combinations and permutations of large sets. Finally, we consider families like the triangular, perfect, and Fibonacci numbers. We also encounter problems like the twin prime or Goldbach conjectures, which remain unsolved despite their simplicity. Mathematics is alive, and these open doors remind us that there is always more to discover.